Yeah, thank you, Christina, also for this nice invitation. And I think we had so far a very productive discussion. I hope I can contribute a little bit to this. So this, of course, this is a very, oops, this is already the wrong button. This is a very broad field. So until almost the end, I was not completely sure which topics I will cover, but I oriented myself a little bit along the discussions that we had, and I want to add to these discussions via these points here. So I will start with a short introduction, although here I can be rather short because it has been flashed several times already, of the non-abelian Liouville equation. And then I will talk a little bit about the collision terms and their role in dynamical decoherence. And then about one thing we did recently with Damiano and Georg on the missing energy in the inhomogeneous kinetic equation. And then 2 or 3 years ago, I did some numerical toy model simulations where one of the aspects was the role of matter refraction in these oscillations. And I want to give some hints or some results on that. And then I end with some outlook. So just to remind you, also, I think yesterday there was a question about how such objects are defined when they have both coordinate and momentum variables. So this is usually defined through so-called Wigner distributions. So in the Wigner distribution, you basically, the creation and annihilation operator are not taken at the same argument, but they are shifted. And then this is folded with an exponential over, in this case, the offset in the position. And then you get some function that depends on the coefficient in this exponential, which is the momentum in this case, and the center position, which is R. And so this is the definition. You can also write this in, so here it's written as an integral over location operator, but you can also write it as an integral over a momentum offset, in which case these creators and annihilators are just defined in terms of the momenta. So these are equivalent, it's just Fourier transformations. And of course, you can do this for neutrinos and also antineutrinos, and you can introduce different flavors. They are here denoted by indices I and J. Right, then usually apart from source terms, the Liouville equation looks something like that. So on the left-hand side, you have this time derivative plus convection term. Actually, here the question will be, what is this exactly? Is this just a scalar, or is it also a matrix? We will come back to this when we see better where this equation comes from. And then on the right-hand side, you can have basically a commutator, which is which includes vacuum terms, matter terms, and self-interaction terms, and of course, potentially also collisions, which here I haven't put. So then, for instance, for the self-interaction, you can write it like this. This is a matrix of coupling constants. So for instance, if it's only neutral currents, it will be diagonal. It can be put as the unit matrix, in which case you actually can forget about this because it's the identity. But this can also be used for non-diagonal interactions. For instance, if you consider the mixing of active and sterile neutrinos, then one of the entries for the sterile neutrinos will be a 0, and this equation is still valid. Yeah. Okay, and the same for antineutrinos with some small sign modification, which I don't go into it. Now, this is a general shape of the Liouville equation, and how does it now generalize to the case where you have flavor mixing? Then essentially on the left-hand side, you get these anti-commutators. It looks like a Poisson bracket, so to speak, in classical mechanics. And you see these two combinations, either a gradient of the density matrix anti-commuted with the derivative of the Hamiltonian with respect to momentum, or the other way around, and there's a relative sign. And then also you can have a collision term. Yeah. So now this is already answers you the question, so basically when you have, let me put it like this. if you look at the first term here, if only the kinetic term of the Hamiltonian depends on momentum, then this is essentially a velocity. In fact, it's a group velocity, not a phase velocity, and that's different from the right-hand side. On the right-hand side, usually, for instance, in this vacuum term, you have phase velocities and not group velocities. So on the left-hand side, the group velocities appear, and in principle, they can also be a matrix now because, of course, you know, the Hamiltonian will have a mass matrix, which is not necessarily diagonal, and then this, what you call the velocity, is itself a matrix, so to speak. Yeah. So if you have, for instance, if you diagonalize in the mass, it will have this structure, of course. And the physical interpretation of this term is it's a matrix of neutrino fluxes. The last term here is a force term because this is the spatial derivative of the Hamiltonian, so the gradient of an energy, which is a force. And so often it is neglected. You can show that it's usually also in the supernova context is totally negligible. Although we will see a counterexample when it comes to this missing energy where it does actually play a role. So if you have no mixing and no forces and no collisions here, then this Liouville equation just expresses flux conservation, because then this is basically the flux of neutrinos with different velocities if they have different masses. Okay, now this is, so the question is now, how do you derive this equation in a general way? And one thing is, of course, that you go into the Heisenberg picture where the operators become time dependent. And so you have the Heisenberg equation for operators like the A's and A daggers, and also the B and B daggers for the antineutrinos. And they usually fulfill these kind of anti-commutation relations. And if you do now a detailed calculation and you define these bilinear operators where you combine a creator and an annihilator at different momentum variables, then you can define again a Wigner transformation, but this time it's for an operator. So this is basically an operator at location R and momentum P. And if you make an ansatz for the Hamilton operator, that it's a bilinear in creators and annihilators with a C number matrix in the middle, then if you solve this Heisenberg equation, of course, there's a bit of a lengthy calculation, but you can do this, then in the end, you get this equation. And note here, this is still an operator. The H here is a C number matrix. And here you have some strange things in the exponential. And this is called a Moyal equation here. And so far, there is no approximation involved. But this is an operator equation, so it's not yet very useful. Okay, here I have also, you see this R and P. Whenever you see two arguments appearing, they are defined through a Wigner transformation the usual way. Now, in order for this to be useful, you have to somehow go either to mean field theory, or maybe you even talk about correlations between different momentum modes, then you get this entanglement. But here we only do the mean field approximation. So now we go from these operators to their expectation values, assuming that there are no correlations between different momentum modes. And then you can, then you can expand these exponentials. And to first order, you get this equation. And that's exactly the one that I advertised in the beginning. So now these rows are C number matrices. These are expectation values. And you get this equation of the Liouville type. And on the right-hand side, to first order, you don't have a collision term yet. You only have refractive effects. I want to point out one interesting thing, which is, you see on the left-hand side, I have kept here, well, in this equation, I have kept the H bars, which are often put to 1, but here, in order to see the role of quantum mechanics, I have kept them explicitly. And you see on the left-hand side, you have an H bar. On the right-hand side, to zeroth order, you don't have an H bar, but to first order, you also have an H bar. So the H bars to first order cancel. And that's why the Liouville equation to the lowest order is actually a classical equation because there is no H bar here. Yeah. Then higher orders, so if you expand this, say, to second order, then you get other things, in fact, in particular, collision terms and other quantum corrections. And yes, so this I already said. To first order, the H bars cancels, and to higher order, of course, you get the quantum effects. Now, okay, this I will skip because there's not so much time. You can actually do this, derive this equation yet in another way through so-called Husimi distributions, which are another, well, it's a kind of Wigner distributions that are folded over Gaussians. And then you can even make a connection to wave equations, but I will not go into this, but in the end, you again arrive at this structure. In this case, I have now neglected flavor effects. And the point is that you always get back. So if you start from a wave equation, this is the Schrödinger equation for the operator, and you go through these Husimi distributions, in the end, you get back to lowest order, the classical Liouville equation. So the message is there's a very interesting connection between wave equations and Liouville equations in the lowest order. Okay, now let me come to one of the higher order effects, which is the collision terms. And in our old 93 paper with Georg, we derived this, and it has, so this is a scattering term on the background medium, and it has this structure. You see actually what you would expect. So if you have only one flavor, then these are just occupation numbers, and you see these Pauli blocking factors here, as you would expect. And these are structure functions of the medium. So in some sense, these are rates of transition when you exchange momentum between P and Q. So this depends on the structure of the medium. Usually you scatter on nucleons and on electrons, and you can calculate this. I have not put the equations for these omegas, but you can, these W's, but you can calculate them in terms of the medium. They may be quite complicated, but in fact, there's also some interesting thermodynamic aspects, because if the background medium is in thermal equilibrium, there are non-trivial relations, detailed balance relations between these coefficients that play a role when you consider thermodynamics. I will talk a little bit later about this later. There's also, it's interesting to understand physically these different terms. So these first two terms, they are basically just scattering terms, but you also see here terms with 2 powers of 1 minus rho, or 2 powers with rho, and these are clearly annihilation or creation, pair annihilation or pair creation effects. And in fact, they are related to these scattering terms by crossing one neutrino on the other side, then it becomes an antineutrino, so there's a tight correspondence between. You have to go, for instance, from the 4 momentum P to minus P, and from rho P to minus 1 minus rho P bar, where this is the quantity for the antineutrinos. And then you can basically reconstruct these terms directly from the scattering terms. So they are not, in some sense, not independent. They are necessarily there if you have a medium that's in thermal equilibrium at least. Now, so this was the neutral current term. So this is why, sorry, this is why this is called NC. We of course have also charge current interactions, and they produce neutrinos. They could also produce Pair-Bremsstrahlung, which I have not included here. But in general, these charge current terms have the following structure. There are anticommutators of some production rate with either the density matrix or 1 minus the density matrix. And in fact, again, if the medium is in thermal equilibrium, there's a detailed balance condition between these two coefficients, and you can put them together in this way, which is very easy to understand. This is basically just a production rate multiplied with a Pauli blocking factor, where this F0 here is the equilibrium occupation number. Yeah. So this is in some sense, the charge current interaction term is much simpler than the neutral current interaction term because it's just this anticommutator and there's only this one term. Now, there's also some interesting thermodynamic aspects of all that. You can define the internal energy of the neutrinos, the lepton number, and the entropy. I think this equation has been already shown once or twice. And in the most general case, you would construct a so-called grand canonical potential, which is this combination. And now, using all these collision terms and the Liouville equation that I showed you, you can show that in the most general case, this grand canonical potential can never increase in time. It has to decrease. So basically, the derivation, well, okay, the simplest case is actually the simpler cases when you have, for instance, only neutrino self-interactions, no interaction with the background medium, because then the lepton number is conserved, and also the energy in the neutrinos is conserved because you don't exchange energy with the medium. And then this is, of course, equivalent to saying that the entropy can only increase, yeah, because these two terms are constant. And if this decreases, the entropy has to increase. And the derivation of this is, in fact, very similar to the so-called Boltzmann H theorem, which is usually computed by using this assumption of molecular chaos, so that you have different interactions that are uncorrelated if they take place one after the other. And the derivation is very similar, with the one difference that now, of course, here these rows are not occupation numbers, but they are flavor matrices. But the derivation goes through almost in the same way. The only thing, of course, one has to do is one has to pay attention to the order of these matrices because they don't necessarily commute. Okay, so maybe not too much detail here. So the essential thing I already said. Sorry, it's time. Okay. There is time. Okay. So one thing maybe I also want to stress here. So in the simplest case, where you can consider entropy because lepton number is conserved and internal energy is conserved, you can even show that the only way where the entropy is not growing is the case where the system is already in thermodynamic equilibrium, which means that the density matrices equal the equilibrium occupation numbers. And in this case, actually, you can see it, for instance, from here. Yeah, if the density matrix equals this, then of course this whole thing vanishes and there is no collision term anymore because creation and absorption just balance each other. And similarly for neutral current interactions, and only in this case, entropy is already maximal, so to speak, so it cannot grow any further. And you are in equilibrium in the sense that the density matrices are time independent. But if you are not yet in equilibrium, you keep increasing the entropy and you're approaching, so to speak, equilibrium in the neutrino system. Okay, now comes to the next topic, which is related to this work with Damiano and Georg. So one thing you can do is, so if you have neutrino self-interactions, they will contribute to the refractive energy. And it turns out that this refractive energy, which we call U oscillation, can be written in this form. It's of course first order energy Fermi because it's a refractive term. And this, I forgot to put this down. These are polarization vectors. They are basically just the expansion. Again, sorry, I didn't put all the assumptions here. I assume two flavors. Then the density matrices are just Pauli matrices, essentially. So if you expand the Pauli matrix in polarization vectors, then these are these objects. And you can express the oscillation energy in terms of these polarization vectors. So one thing is, for instance, if you have a totally incoherent superposition, the polarization vectors would be 0 because rho would be 1/2, 1/2, or 1/1. Yeah. And then, of course, you have no contribution to the oscillation energy because nothing oscillates. Yeah. But if you have a fully coherent system, the lengths of the polarization vectors become maximal. Usually you use the normalization where the length is 1. And then, of course, these terms contribute. Now, I think, I mean, Damiano did most of the work there. And I think he started out by doing a numerical simulation of the evolution of the system and the oscillation energy, and he found that the oscillation energy is not conserved, which was first a little bit surprising. And in fact, it's not a small effect. So you see here that if you compare it to the absolute value of the oscillation energy, it's a variation of order 1, yeah, because it goes from -1 to plus 0.5 or so. So it's certainly not a small effect. Then what you can do is, using the equations of motion, you can even derive a time derivative of this oscillation energy. And what is interesting is that on the right-hand side, only gradients appear. So in other words, if you have a homogeneous system, the energy is conserved. Then there is no problem. But if you have inhomogeneities, which in some sense is the more interesting because more realistic case, then you break this conservation of this energy. By the way, yeah, so there are some notations here. There's P0, P1. These are just the polarization vectors weighted with the case power of the velocity. So this is this K index. So this would be just as, if K is 0, this is just the sum of the polarization vectors. If it's 1, it's weighted with cosine theta, which is in the Z direction. Typically in a supernova, where you have the radial direction, it would be basically the projection of the radial direction. Okay, now the question is, where does this come from? This energy, this change of energy. And Damiano did very detailed calculations. And it turns out, so now for simplicity, we use the massless limit here, so that this velocity has absolute value 1, because they move with the speed of light. So the left-hand side of the Liouville is kind of trivial. It's just the advection term and the time derivative, of course. And now on the right-hand side, you have the refractive effects, but also a force term. Apart from this, this is actually the divergence of a flux. So this would be just flux, neutrino flux conservation. But there is also this force term that is usually neglected. And it turns out that this force term can be written in this form. And again, it depends on gradients of the density matrices. And then one can show that with this force term, the total energy is basically conserved. And now you can ask, where does the energy come from that sets off this variation? It turns out that it comes from the pool of kinetic energy of the neutrinos. And since I have here assumed that they are massless, the kinetic energy is just, you know, the integral over the momentum, because energy is momentum in this case, times the trace, so the total number of neutrinos in the modes P, and then of course summed over all momentum modes and integrated over volume. So basically, the variation of the oscillation energy comes from an exchange with a pool of kinetic energy, which is actually much, much larger. Yeah. So it's enough. So the effect in terms of the oscillation energy is big, but if you compare it to the kinetic energy, it's very small. Yeah. So it's enough to put a very small fraction of the kinetic energy to explain, to put in the oscillation energy, and then the total energy is conserved. Okay, now last topic. I'm running out of time a bit, but this is, I think I go not into much details. So I think, here's the reference. In 22, I made some numerical simulations, but it was a toy model. I was not attempting to do any realistic supernova model because, and here I think we have a discussion with Irene, because I think the real case you cannot resolve because the scale, the hierarchy of scales is too big. So I just resorted to a toy model, so to speak, but by trying to keep with a hierarchy of rates that is motivated by the supernova. So lambda is the matter refraction term, mu is the self-interaction refractive term, and then we have certain rates for charge current. Sorry, this should be CC here, for charge current creation and absorption processes, and for neutral current scattering. And so the biggest term is the matter refractive term, then comes the neutrino self-dispersion, so to speak, and then the collision rates. And then, okay, now I think I will skip most of the details. So what I've done is here, the highlight, I have assumed two flavors I have only considered one energy, so no difference in energies, and one spatial dimension, which is supposed to be the radial direction in a supernova, and basically a one-dimensional array of a certain number of momentum modes. And the velocity projection on the radial direction is put isotropically between -1 and +1. So I have this, basically this velocity here, which is just a linear function of the bin. You don't have to write, you don't have to read the details. And then I have certain ansatzes, because now I have one spatial dimension, so I have to put it up in the appropriate form. I have a vacuum term, I have a meta term, which is this lambda, and I have a self-interaction term, which has the structure that I showed you earlier, with some coefficient mu. And now the point is, the point of my study was that all of this can be inhomogeneous. So it can depend on x, on the spatial coordinates. Now there are these coupling constants. They go roughly like 1 minus the product of two velocities. This is just a normalization factor, so the details don't matter. Then what is actually important are initial conditions and boundary conditions. It turns out that in this business, the boundary conditions play a very important role, because the results can depend a lot on those. Now, in this case, so these are too many equations, but basically this is an initial condition. And since I was mostly interested in fast flavor conversions, I have often put the masses to 0, but then you have to seed the system by some slight tilt from the z direction. So instead of using a mass for the neutrinos, I have put something that is not exactly an electron neutrino, which would be exactly the z direction, but something that's tilted. So this is the cosine of theta is something very small, like 10 to minus 4. It serves as a seed, basically, to start flavor oscillations. Then I have also modeled a so-called electron-lepton number crossing as a function of the angle, because we know that this is essential, or it can be essential for triggering fast oscillations. And you know, there are many details that I don't go into. Actually, it turns out that, yeah, sorry, let me first say, so about the boundary conditions. So the outer boundary, I have assumed that basically nothing comes in, only things get out, because you have something that's emitted from the supernova, so it should not be that you have negative velocity modes. But it turns out that this is not totally trivial, because the boundary conditions have to be consistent with the initial conditions. Yeah? And I spent significant thought on that, because mathematically this is sometimes not totally trivial. So in fact, I have a small term of neutrino flux coming in, but it's much smaller than the one coming out. And on the inner boundary, I have reflective boundary condition. The motivation for that is that if in the inner boundary, you're within the neutrino sphere, so everything should be more or less isotropic. And so the neutrinos flowing forward and the neutrinos flowing backward should basically be the same, because everything is isotropic. And that motivates the reflective boundary conditions.
Sorry.
Yeah. Yes, exactly. This is this equation here. So if it would not be a mixture, then mx. So for instance, if I put, so theta is the polarization. So if theta is 0, then it would be just 1, 0. Yeah, so the pure electron flavor. But here I have assumed a small theta so that I can start the oscillations without a mass term, so to speak. I have also done some simulations with a mass term, but I wanted to focus on this, so not to depend on the mass terms. Okay, now, sorry for the many equations. I plot a number of things. So what you can see in the following plots are the total number of neutrinos. So this is summed over the momentum modes at each position and each time. The off-diagonal terms and the total flavor asymmetry of outgoing neutrinos. I'm only interested in outgoing neutrinos because this is the only thing I can observe, because eventually I want to detect a supernova, and of course I cannot see the neutrinos that are going into the supernova. So I sum this asymmetry over modes with velocity in the x direction larger than 0. Sorry, this should be here downstairs as an index. And also, I can plot the relative flavor lepton number asymmetry. So this is related to these angular crossings. And now I show you a couple of, well, this is a list of, sorry, this is a long list of the simulations that I did, but just to highlight, I will show you 4 cases. These are these underlaid shaded cases. And you see, for instance, here, in these cases, the mu and the lambdas were the same. They have a profile. I've assumed an exponential profile because one of the focus of this study was inhomogeneous cases. So that's why I have these profiles here. And then in the first 2 cases, there are no scatterings. And in the last 2 cases, there are scatterings of various strengths. And I want to see how they influence the oscillations. So now let's look at this. So again, a bit busy plot, but this is the outgoing flavor asymmetry. And you see at time, the time is on this axis, the x is on this axis. So you see here, at t equals 0, you start with maximum asymmetry because you start essentially with an electron neutrino. Yeah, and then you trigger the oscillations, and then you see that at a certain x, after some time, you have flavor conversion. It goes actually to 0. This is an almost maximal mixing here. But at large x, which is far away from the neutrino sphere, it takes longer. Yeah, which makes sense because the refractive terms are much smaller, so they take longer to develop. Eventually, you will have these flavor conversions at large distances from the neutrino sphere as well. And this is due to a combination of the local refractive effects and the convective term, which transports the converted flavors outwards, so to speak. Yeah. So this is basically the qualitative explanation of that. Okay, the rest is not so important. These are cuts through this at different axes. So you see, for instance, at different axes, the innermost axes convert very fast. The outer ones, you have to wait for a while until this transition is triggered. So this was the first case where you have only self-interactions and nothing else. So this is the pure fast flavor transition, so to speak. Now what I do in the next case is I switch on a meta term of equal strength, and you see it has a modification. Generally, it turns out that the conversions are still happening, but they are delayed. Yeah, and this is one thing that I found interesting because often it's argued that the meta term can be rotated away, so it should not play a role. But in this case, it's not the case, and in fact, it's well. I think in the homogeneous case, you can often rotate away the meta term to good approximation. It's not a mathematical identity, but if there's a hierarchy of scales, you can rotate it away. But in the inhomogeneous case, it's not possible mathematically. And actually, the reason is very simple, because the point is that the meta rotation, this lambda term, is a local rotation rate, but it depends on location. So there is no global rotating frame that you can put yourself into to transform this away. Yeah. So this is the reason why you cannot just transform it away. Now, of course, you can argue if the variation of the meta term is slow enough, you can always locally create a rotating frame, which allows you to rotate away. But even when it's more or less adiabatic, I still found a significant effect. So this one, now I don't remember how adiabatic this was. I think it was just on the limit of being non-adiabatic versus adiabatic, but you still have a significant effect of the meta term. In this case, it tends to delay the onset of the flavor. What is plotted here is the outgoing flavor asymmetry. So, yes, okay, this electron, yeah, sure. This is proportional to the electron-lepton number in charged electrons, yeah. So actually electron minus positron density, yeah. 5. Okay, I'm not far from the end, so don't worry. So now, what about the neutrino term? This is included here, yeah. So in fact, this is now, right, in the second simulation, it's both. And in fact, as you can see from this table, they have equal strength in this case. So I told you in the beginning, the supernova, the lambda actually it tends to be larger than mu. But in fact, some of these simulations are quite delicate. Some of them just break down because of numerical non-convergence or just breakdown. So I could not afford, at least in this setup, to have a lambda that's much larger than mu. Then the simulation just didn't work. That's why in the end I chose something that's comparable. Okay, so now, so these two cases compare pure self-interactions with self-interactions plus meta term. Now I switch on a scattering term. So this is here, but the rate is much smaller. It's given by this expression. And you see, again, it has an effect. And in fact, it has even a stronger effect, a delay here. So in the inner part of the system, the conversion still takes place. But in the outer part, it's basically either not there or it's very much delayed. And even up to the maximum time that I simulated, you hardly have any conversion. So the message is this combination of meta term and scattering term does significantly influence the fast conversion. Now, an extreme case where I have both meta term and scattering term, and in this case, I can even totally suppress the fast flavor oscillation. So here you see nothing happens. You see it on the scale here. Basically, it's just a lot of noise. And in fact, these are the off-diagonal elements. They are damped to zero because nothing happens, basically. Yeah. The only thing that happens is that the neutrino number is a function of x, just because because of the dilution of the profile. But essentially, there are no oscillations happening. You can also plot the flavor number asymmetry as a function of the cosine theta, so of the velocity. And just because I'm running out of time, maybe just show you this example. These are for the 4 simulations that I just showed. This is at x equals 0. This is where the neutrino sphere is in my little toy model. I start with this crossing. So in absolute values, it's a small crossing. And after some time, sorry, I should look at the green and the red curve. So this is not at x equals 0. I'm sorry, this is at x equals 5. So I start with this. And after some time, the magnitude of the crossing is diminished by these effects, which is what you would expect because you have scattering and you have a meta term which tends to even out these crossings, but not totally. So still something remains, but the crossing is basically influenced. So now I come to the conclusions. So there were basically 2 parts. I have 2 slides on the conclusions. The first thing, which I could not cover completely, but I hope I was able to give you a taste. There's actually a deep connection between Schrödinger-like equations for the wave operators and the classical Liouville equation. And you can also generalize this to Vlasov-Boltzmann equations with collisional terms. This was this discussion we had with Tobias Stirner and Georg Raffel a couple of years ago. The classical behavior in this analysis emerges on length scales that are large compared to the de Broglie wavelengths. Yeah, so this is important whenever you have these Wigner distributions, you have to have a separation of scales. So that means that the spatial scale on which things vary has to be much larger than the characteristic inverse momentum. So this is basically a separation of scales. But in the lowest order, in an expansion of H bar, you have this classical behavior emerging where the H bar cancels out. Yeah? And in this order, one has the collisionless particle transport and kinematic decoherence. Actually, I think I totally skipped the thermodynamics discussion. No, I did not. I showed you, but I forgot to mention the difference to kinematic decoherence. This also leads to a lot of confusion, in my opinion. So when you have no collision terms, you still have, because you have modes that oscillate with different frequencies, so they can decohere, right? Because you superimpose them, and then things look like they would oscillate out. And sometimes this is interpreted as a loss of coherence, but it turns out that it's not it's not linked to any change of entropy, because in principle, if you wait long enough, you could have recurrence effects, and the whole information is still there. Only if you do scattering, non-forward scattering, you have loss of information, like in Boltzmann's HDRAM, and then you have real kinetic decoherence, so to speak. Yeah. Then in this expansion in H bar, the higher order terms would describe correlations between momentum modes and the collision terms and the dynamic decoherence, as I said. And okay, this you know, the forward scattering term is the foundation for all collective effects. And this was the discussion we had with Damiano. The self-induced exponential growth of small inhomogeneities violates actually conservation of the refractive energy from the neutrino self-interactions. And this can be cured by a force term that leads to energy exchange between the neutrino kinetic energy pool and the refractive term. I should also say in practice for supernova simulations, this is kind of negligible because the energies that vary are so small that they do not play a role in supernova simulations, but this was more a conceptual question, yeah, because of course, if you have consistent equations, they should better conserve energy. Then the last part was about some numerical study, and here maybe the main conclusions are one can construct these toy models to understand the interplay between self-interactions, matter, vacuum, and source terms, as well as boundary conditions. And maybe we can discuss the discussion, and we can continue the discussion. I don't see a way how to do this in a realistic setup where you have a full, supernova profile, because then you under-resolve, at least in radius, you would under-resolve, in my opinion, the system. But maybe due to some subtle effects, this can maybe, if you reach some kind of local equilibrium, maybe there's a way out, but I have not understood it yet. What I found in this toy model is that boundary conditions and consistent initial conditions are important, and sometimes they're not even completely straightforward when you do this numerically, but they certainly influence the solutions that you get out. Then one thing I found is that the matter terms cannot be trivially rotated away in general, especially when you have profiles with significant slopes. And it may depend on some adiabaticity parameter, but this is also not fully understood yet. And then the fast flavor conversions tend to be suppressed or at least delayed in the presence of inhomogeneous matter terms and neutral current non-forward scattering. Okay, and then I stop here. Thank you.
Thank you very much for this very clear talk. I have comments first, maybe.
One question.
Yeah, may I?
Yeah, sure.
So, first of all, one comment is the fact that in the slide before.
Yeah,
I just want to comment on the fact that the forward scattering is not only the foundation for all collective effects, is also foundation for many non-collective ones.
Mm-hmm.
Because we always underline, emphasize the fact that neutrino-neutrino interaction forward scattering is the foundation for collective, but many flavor conversion phenomena are non-collective. For example, the magnetic neutrino, the matter-neutrino resonance is non-collective.
Okay, yes.
There are several phenomena that are flavor conversion mechanisms that are not necessarily collective.
Yeah.
We have we got accustomed to this jargon, but I think it's important to keep in mind that it's not always a collective behavior.
Do you mean the resonance between matter and self-interaction effect? I think this. Yes. I'm not familiar with that, but I heard about it.
You have an energy-dependent behavior, and the neutrinos do not behave collectively in flavor space. So in that sense.
Okay.
And the other comment I have is in slide 6, if you can go back. Yeah, I think, no, 6, no, 5.
Oh.
Yeah, I just want to say that when one makes these ansatz on the Hamiltonian operator, so that we dagger CH is C number in A, we are already in the mean field approximation.
Yeah, that's true. Yes.
Okay.
Yeah, I should have
said. Otherwise, it's quartic.
Yes. Yeah, no, that's true. In principle, you have even a whole expansion here, even of higher order correlators, but right, this is only the.
This is already mean field.
the mean field part of it, yes. Yeah.
Okay.
Mhm.
Thank you.
Just a curiosity, I mean, in this toy example that you have considered, did you try to understand whether the transitions are adiabatic or non-adiabatic?
The transitions.
I mean, the flavor conversion, is adiabatic or non-adiabatic?
In which sense do you mean? I mean, you mean, so when you have adiabaticity, you compare two rates. Which rates do you have in mind?
Well, I mean, you consider the toy model, right? Where there is a flavor conversion.
Mhm.
And just a curiosity, I'm wondering whether you have looked at whether these flavor conversions are in adiabatic take place in adiabatic regime or non-adiabatic regime or slightly non-adiabatic regime. But this requires, of course, a additional kind of looking in a different way into the transitions. Maybe you did it numerically, you didn't care about.
Yeah, probably. I mean, adiabatic usually is you compare the change of a rate with the square of the rate. Do you mean that? I mean, where the rate is now.
No, usually what matters is the how fast the density changes
Okay.
with respect to certain combination of parameters of the
You mean
oscillations.
the method density or
Right.
Okay. Yes, I think I was actually in the adiabatic limit. I mean, yes, I don't remember the number, but I think it was on the adiabatic side. That's why I was a bit surprised that the meta effect still had a big effect.
Okay.
But I can look up the numbers later. It's actually in the paper, but I forgot what it was.
Okay. Thank you. Maybe I should add that there is a very nice non-adiabatic description of the non-adiabatic transitions, analytic description. That has been used by the Bari group in some time ago, long time ago, in their studies of flavor conversions in supernovae.
Okay, maybe you can tell me the reference. Yeah.
Thank you. Who was Sajjad? Who was raising the hand? I saw somebody. No. No further questions or comments? No. I saw.
It's just a very short comment. The conclusions that you were drawing on the role of collisions in the context of oscillations at the end. So you say they can suppress the oscillations, but you know, we actually showed that actually this depends on the initial angular distribution that you have. So you can either suppress them or enhance them according to the initial conditions that you set. So I agree that this could be one of the cases, but it's not always the case.
You mean this figure that I showed here?
Yeah,
where here it was suppressed, and you are saying it can be enhanced.
Yeah.
Okay. Yes, I think, right. I think I'm aware of that, and I even have a comment on the paper, but I don't remember now under which conditions it can be enhanced. But is this a collisional effect, probably, right?
Yes, depends on
Yes.
which.
Yeah.
Then, because of collision, modify this ELM distribution. Therefore, you can make
Yes.
Suppression of the survival probability.
Is this related to the so-called collisional instabilities? No. Okay. Yeah.
We had a paper with the sums.
Okay. Maybe we can discuss offline. Yes.
Other questions or comments? Okay. So, but not, let us thank you
Thank you.
again.